Welcome to this explainer. Today, we're diving straight into the sheer physics, the insane logistics, and the cutting-edge material science needed to actually pull off a human colony on Mars. We hear about this dream of a Martian city all the time, right? But the massive, multi-stage engineering endeavor required to make it happen is rarely picked apart from start to finish. So, we're going to deconstruct the exact plans, the incredible machines, and the immense hurdle standing between us and the red planet.
Okay, let's kick things off with a totally staggering number. 1,000 to 2,000. That is Elon Musk's ultimate goal for how many starships he wants to send per Mars rendezvous to build a self-sustaining city. And remember, a rendezvous only happens roughly every 26 months when Earth and Mars perfectly align. Think about the scale of that for a second. We're not talking about a quick Apollo-style flag and footprints mission here. We're looking at a proposed interplanetary highway ferrying tens of thousands of tons of cargo and passengers across millions of miles of deep space.
To really wrap our heads around this, here's our mission briefing for the explainer. We'll be walking chronologically through Phase 1, the vehicle, Phase 2, the timeline, Phase 3, transit and landing, Phase 4, the settlement, and finally Phase 5, the return.
All right, Phase 1, the vehicle, because obviously this all hinges on the hardware required to even attempt this unprecedented journey.
It's actually wild to look at how quickly this vehicle's design and even its name have evolved over the past decade as the harsh engineering realities set in. What started out as the Mars Colonial Transporter back in 2012 morphed into the Interplanetary Transport System in 2016. Then a massive design shift in 2017 brought us the Big Falcon rocket, or BFR, before they finally settled on the Starship architecture in 2019. It really shows a company aggressively iterating its designs in real time.
But the absolute game changer of that entire timeline happened in 2018. SpaceX made this radical pivot away from lightweight carbon composite materials straight to 300 series stainless steel. Now, why do that? Well, while carbon composite is incredibly light, stainless steel is significantly cheaper and way easier to manufacture. But most importantly, it performs exceptionally well at the extreme cryogenic temperatures of deep space. Plus, it has a naturally high melting point, which is absolutely critical when you're slamming into an atmosphere.
Moving right along to Phase 2, the timeline. Let's see when SpaceX actually plans to roll out these massive stainless steel ships. Musk has outlined a highly aspirational step-by-step approach. The goal is to send an initial wave of 5 uncrewed starships as soon as the 2026 transfer window. If those successfully land and prove the concept works, the tempo aggressively scales up to 20 ships in 2028, and get this, at least one of those is planned to carry human passengers. From there, the target is 100 ships by 2031. It's an exponential scaling curve that essentially leaves zero room for error.
But, we have to have a reality check here. Given that Starship hasn't even successfully transferred cryogenic propellant in orbit yet, experts, like aerospace engineer Robert Zubrin, are highly skeptical of this immediate timeline. The general consensus among veterans in the field is that while the underlying architecture is incredibly sound, getting a vehicle this complex fully operational on these near-term deadlines is likely unachievable.
Which brings us to Phase 3, transit and landing. This is where we hit some unprecedented technical bottlenecks for the journey itself. Picture this. Before a single Starship can even dream of leaving Earth orbit for Mars, it needs fuel, and a lot of it. We're talking 1,200 tons of cryogenic liquid oxygen and methane propellant for one ship. Getting a completely full load is absolutely essential to reduce the transit time to Mars down to just 3 or 4 months. Why? Because the faster the trip, the less time your human crew is exposed to life-threatening galactic cosmic radiation.
And that creates a massive logistical nightmare right in our own orbital backyard. To get those 1,200 tons into a waiting Starship, SpaceX will need to launch up to 12 separate tanker flights for every single Mars-bound ship. That means those 5 initial ships planned for 2026 would require up to 60 tanker launches. Actually, wait, 60 launches in just a few months? You can see the hurdle here. Plus, they have to master orbital refueling without losing too much super-chilled fuel to what engineers call parasitic evaporation, which is just what happens when cold liquid hits warmer pipes.
Okay, so fast forward, we've made it to Mars. Now the ship faces a truly harrowing entry. Keep in mind, a fully loaded Starship is 200 times more massive than anything we've ever dropped on the red planet. To slow down, it will use a maneuver called aerobraking, relying on entirely untested, reusable metallic ceramic heat shield tiles. And here's the crazy part. The Martian atmosphere is thin, yes, but it's heavily carbon dioxide rich. When that CO2 gets ionized by the sheer heat of entry, coming in at 7.5 kilometers per second, it generates free oxygen that actively eats away at those shield tiles. It is an incredibly punishing environment. Assuming we navigate that landing safely, we hit Phase 4, the settlement. How do humans actually survive the harsh, radiation-bombarded surface? While SpaceX loves to pitch humanoid robots, like Tesla's Optimus, building infrastructure, academic researchers are leaning towards a concept called D2RP, or Design to Robotic Production. This is a fascinating method, using swarms of highly capable, autonomous rovers to excavate the ground and essentially 3D print habitats for us using the Martian soil itself, long before humans ever arrive.
And the reason we absolutely must dig underground is simple. The surface of Mars is bathed in deadly radiation. By using robots to excavate a spiraling, rhizomatic structure reinforced with local regolith concrete, we gain instant natural protection. An underground habitat like this insulates the crew from galactic cosmic rays and those massive temperature swings of the Martian day-night cycle. It's basically a natural fortress carved directly into the planet.
You can see how this works in reality with the D2RP processes currently being tested right here on Earth. Robots 3D print a structurally optimized, highly insulated shell. On Mars, this 3D printed concrete layer acts as a rugged outer barrier. Inside that barrier, you'd place a softer, inflatable, pressurized environment where the crew would actually live, breathe, and grow their food. It's a brilliant two-layer system.
Finally, Phase 5, the return. We've got our sustainable underground base, but eventually astronauts need to come home, right?
Here's the kicker. Bringing return fuel all the way from Earth is flat out impossible. It is simply too heavy. So the entire mission architecture relies on ISRU, in situ resource utilization. That means mining the Martian environment. Specifically, we have to pull carbon dioxide out of the thin atmosphere and mine water ice from beneath the surface to manufacture liquid oxygen and methane propellant directly on Mars.
The chemistry behind this is honestly beautiful in its elegance. It's called the Sabatier reaction. You take that atmospheric carbon dioxide, mix it with hydrogen that you've split from the Martian water ice, and you get a simple, almost risk-free chemical reaction. The output? CH4 and H2O. And that CH4 is methane, literally the exact fuel those Starship Raptor engines are designed to burn.
But, and there is always a but, doing this at scale comes with a massive energy requirement. Splitting water and running chemical plants takes a colossal amount of electricity. Estimates suggest it's going to take roughly 600 kilowatts of continuous power just to produce the 600 tons of liquid oxygen needed to fuel up one single Starship for its trip back to Earth.
So where's all that juice coming from? Well, SpaceX is eyeing solar power, but to generate 600 kilowatts on Mars, you'd have to roll out about 38,400 square meters of solar arrays per ship. That is roughly 7 American football fields of delicate panels that have to be installed and maintained in a super dusty environment. On the flip side, NASA traditionally prefers nuclear fission reactors. They give you continuous, reliable power and require way less mass to transport. The catch? They introduce incredibly complex political and safety hurdles here on Earth before you can even launch them.
As we wrap up this explainer, we really have to look past the rockets and the chemistry, because the ultimate hurdle might not be the engineering at all. Even if the physics perfectly align, establishing a multiplanetary footprint requires a sustained astronomical budget and unwavering government partnerships that have to span across decades. It leaves us to wonder if shifting political winds and economic realities will ever allow this incredible Martian journey to truly leave the launch pad. What do you think? Will our collective willpower ever match our engineering prowess?